So here is where we were looking at the BCJR algorithm with extrinsic input and output and how does it work, and looking at the expression it is clear that the second part. So once again I think there was a question about what this u and v are. So basically if you have a branch, there will be a label on the branch, okay, this is S prime and this is S, and the label on the branch is basically S prime S, that is the input in stroke, and there will be an output, right. The output is basically V of S prime S, okay. So that is my notation when I say u and v, okay. And clearly the second part here does not use any extrinsic information, it is just it uses only channel, okay, uses channel values, okay. And the first part is where we have to really use the prior information, okay. So how do we do this? It's not too hard to imagine how you can do this. If you get if you look at the nth stage, okay, so I think the picture somehow every time I do this the picture gets to the bottom of the screen, and wait, let me see, like I can do this also, okay, okay. So what is happening in our turbo kind of situation? So you have so this is maybe BCJR1, okay. If this is BCJR1, your RL is going to be what? YSL and Y1L, right. This is if this is BCJR1. If it is BCJR2, then this is going to be YSL will be the same, and then it will be Y2L, right, that is RL, and V and U are kind of going to be the, so U of S prime S, those things depend only on the branch, okay, so you can't say much about it. And what is the extrinsic information coming in, okay, so you would have had LE1 or LE2, LE2, okay, so LE2 which will be, let us say, just for simplicity of notation I will simply say L0, L1 all the way to, okay, I don't want to use L because I have to use subscript L also. So what can we use here? Be delta, okay, delta 1, delta 0, delta 1, so on, right. You will also have a delta L, okay, all the way to delta, let us say k minus 1, maybe something more, okay. So that is how LE2 will look, and this is basically the extrinsic information. And what is this, how should we think of this? This is basically log, okay, of a ratio, the ratio of what? Probability of UL equals 0 divided by probability that UL equal to 1, okay. So this is how, okay, so given, okay, all that is given, but this basically I am going to think of the extrinsic LLR as some log likelihood ratio, and remember this is extrinsic, okay. So this probability basically means it does not use anything else, so it is extrinsic, okay. So now if U of S prime S is 0, then what should I put here? I have to compute P of UL equal to 0 and then substitute that there, okay. So from here easily you can see that the a priori probability for U of S prime S equal to 0 for a branch which corresponds to U of S prime S equal to 0, what will be P of U S prime S? It will be e power delta L, what will it be? E power delta L divided by 1 plus e power delta L. Okay, you can show this quite easily, okay. So P of UL equal to 0 is e power delta L times P of UL equal to 1, and if you add those two up it should be 1 equal, it should be equal to 1. So you put that in, you are going to get this. Is that okay? E power delta L by this. On the other hand, if U of S prime S is equal to 1, then what will be this? 1 by 1 plus e power delta L, okay. So let me write that down also here. If this is equal to 1, this guy becomes 1 by 1 plus e power delta L, okay. So that is how you use the extrinsic information. Is that clear? Okay, so it is easy enough to use the extrinsic information. So how do you compute the extrinsic output is the next question, okay. So for that we have to look at the gamma a little bit more closely. So, basically we are saying gamma of S prime S is nothing but P of U of S prime S, here is where we use the extrinsic information, times P of RL, which is P of YSL comma Y1L given what? Given V of S prime S. So, I have to split it into 2. So, how do I do that? We can do it this way. So, it does not matter. So, S is showing up in too many places. So, I will simply say V1 V2. Okay. So, it is for S prime to S. Okay. So, I am just swallowing the notation here. This is basically V of S prime S. Is that all right? So, what will this be? This will basically be 1 by 2 pi sigma squared e power YSL minus what? Okay, so to write V1, I have to basically make V1 and V2 the BPSK encoded versions, right? So what can we do there? 1 minus 2 V1. So do I have a notation for that? I think.
R is nothing but y to z. So is it R minus y1 something?
Y is basically my received value. Okay, so V1 V2 is basically now in bits. Okay, it's 0 or 1, and when I write minus here, I have to write 1 minus 2 V1. Okay, so maybe we can let 1 minus 2 V1 to be what? W1.
Y was
1 minus
oh, y was 1 minus 2 V1 is it?
This
and
was RL.
R
is the received value.
Oh my god.
RL is RL.
Somebody should have told me this. Okay, so we had RL and RL1, is it? Okay, sorry for that. Okay, so but anyway, it doesn't matter. So it's hopefully it's clear to you. Okay, maybe for the recording I might have to redo this lecture with the different notation. But anyway, so 1 minus 2 V1 is basically the BPSK encoded version of V1, right? So there's also another way to write this. I think you can also write it as minus 1 power V1, right? So anyway, so all these things doesn't matter. So I'm just trying to think of a very easy notation for this. So what can we do? Any ideas?
we can assume V1 V2
as minus 1 plus 1. Yeah, it's too many. So maybe let me just keep it as 1 minus 2 V1. Okay, so it's not too bad. Squared plus what? YL1 minus 1 minus 2 V2 squared. Of course, this everything is divided by there is a minus overall also. So this is the formula. Okay, so maybe there's a neater way of writing it. So usually what people do is they would write like this. Okay, so 1 by 2 pi sigma square e power minus, they will put a 2 bars, and that means like norm. Okay, and then what they would do is they simply write RL minus V squared by 2 sigma square. So that's also some other way of writing it. But anyway, so that's just it's irrelevant. So that's the form for the other part. Okay, so clearly the channel received values enter into the second term. Okay, and the a priori values, the extrinsic values enter into the first term. So that's all. That's the main lesson here. Okay, so once you have that, we can now go ahead and compute the final LLR. Okay, so what is the output LLR for stage 1? Okay, for stage L, in stage L, you are going to now add up over S prime S such that U of S prime S equals 0, then you divide with summation S prime S such that U of S prime S equals equals 1, right. So, this log also, I am sorry, log, and then what happens there is you have an alpha term, okay, and then you have a gamma, and then you have a beta term, right. So, let us write that down. There is going to be an alpha L minus 1 of S prime, okay, gamma L S prime S, and then beta L S. okay, and then you have an alpha L minus 1 S prime, gamma L S prime S, beta L S. Okay. So, whether it is intrinsic or extrinsic or anything at all that is going to be part of only gamma. Okay, alpha and beta will generally multiply anything that you put in there. Okay. So, we have to only substitute for gamma. Okay, what are we going to put for gamma? P of, here I am going to put P of u S prime S. What is that in the numerator? U S prime S is always 0, right. So, it is going to be simply P of the a priori 0 times some e power term. Okay. So, e power something. Okay. So, let us keep it like that. Okay. And in that e power something there will be two things. So, I will come to that later. Okay. So, here you have what? P of 1 times e power something. So, already you see there is something that is emerging. Okay. So, there is some simplicity here. So, P of 0, okay. There is one simplification that is already kind of possible here. Okay. So, we will come to that. Okay. There is some common things that will come out. Okay. So, P of 0 by P of 1 will come out. Okay. So, log P of 0 by P of 1 anyway is the extrinsic. So, the extrinsic is coming out by as an independent factor. So, now we have to see if there is anything else that will come out as an independent factor. Okay. Right. What else do you expect as a factor that is going to come out? Okay. The extrinsic has come out already, P of 0 by P of 1, and from the e power part what do you want to come out? Anything that depends on the ys part has to come out, right. And when I want to find the extrinsic output, what am I trying to find? I am trying to get rid of the LE2 part. Okay, that I am able to already get rid of with just the first simplification. Next I have to get rid of whatever depends on ys. The question is, will anything that depends on ys come out of that gamma, the branch metric. Okay. So, P of 0 by P of 1 anyway comes out, and then I have to look at what is in the exponential. So, let us look at what is in the exponential. The exponential will have minus, I will simply write it as ys. Okay. So, it is maybe clear, ys minus what? 1 minus 2v1 squared minus y1, right, minus 1 minus 2 v2 squared by 2 sigma squared, right. So, this is the expression that we had. So, now if you try and simplify, what is going to happen? Okay, what are the various things that are going to happen? Ys squared is going to come, but there will be a similar ys squared term in the denominator. Okay, and that is going to cancel with this, right. And then what else will you have? You will have a 1 minus 2 v1 squared. What will be that? That will always be 1. Okay, and similarly in the denominator, whatever v1 or v2 is, that is always going to be 1. Again, that is also going to cancel. So, the only thing that will be retained, that you have to retain here is 2 ys times 1 minus 2 v1 by 2 sigma square. Is that right? Okay. Is that clear? Okay. So, you will have a similar term in the denominator also, and that you have to retain. Similarly, in the second part, okay, you will have a y1 squared, the denominator also you will have a y1 squared term. Okay, and then 1 minus 2 v2 squared will also cancel with what is in the denominator. What you have to retain is 2 times 1 minus 2 v2 y1 by sigma square. Remember, this v1 and v2 are not the same for each term. Okay, they change depending on what the term is. Is that right? v1 and v2 are not the same. Am I right? Okay. Okay. So, in what happens in a recursive systematic encoder? v1 becomes equal to u, right. So, the u s prime s is 0 means v1 is always 0 in the numerator and v1 will be always 1 in the denominator. Okay, that is the only thing I know. v2 on the other hand will be arbitrary and it will change and all that. Okay, but anyway v2 I do not care too much about, because that is only getting involved with the parity part. I want to only bring out the message, the systematic received value. Okay. So, ignoring this part, not worrying too much about this, if you look at this term, it turns out the only thing that this simplifies to is e power 2 what? okay, 1 minus 2 V1 times Ys by 2 sigma squared. Is that right? Is that okay? And V1 is going to be 0 for the numerator and is going to be 1 in the denominator in my recursive systematic encoder. Okay. So, what will happen finally when I take the ratio, this divided by e power. So, I have to put V1 equal to 0 here, then e power 2 1 minus 2 times 1 Ys by 2 sigma squared. Okay. So, finally, all these things will add up to what? E power 2 Ys by sigma squared. Is that right or not? Okay. So, what comes out? There are two things that come out common in this ratio. One is P of 0 by P of 1, the other is e power 2 Ys by sigma squared. Okay. All right. So, if you do these simplifications, I know I have not done it in very good detail, but go through and look at it and think about each of these steps. It is not too difficult. Okay. So, the first part is P of 0 and P of 1. The second part, what subtracts from Y of s is always either plus 1 in the new, it is always plus 1 for the numerator and minus 1 for the denominator. So, you can pull out the Ys part separately. Okay. When you do that, you see that the final output LLR simplifies to delta L. Okay. Delta L, how did I get this? This is basically log P of 0 by P of 1, that is delta L plus 2 times YSL by sigma squared plus something else, and what will that something else be? Okay, the extrinsic output. Okay. Okay. So, how am I running the BCJR algorithm now with the extrinsic input? Remember there were like 4 or 5 steps in the BCJR algorithm. First step was computing the branch metric, second step was doing the forward recursion, computing all the alphas, third step was doing the backward recursion, computing all the betas, and then the final step was computing the LLRs, alpha beta gamma beta type of thing. Okay. Now, with extrinsic input, the first change is when you compute your branch metrics, you have to incorporate the extrinsic input in this form. Okay. So, your branch metric computation will change. Okay. Does anything change in the second step? Absolutely nothing. What about the third step, computing betas? Absolutely nothing, everything is the same. Then what about the fourth step, computing the total output LLR? Exactly the same, there is no problem. After you compute the total output LLR, okay, which is what comes up here on the left hand side, okay, at the end of the fourth step, you would have computed the total output LLR. Okay. From there, how will you compute the extrinsic output LLR? You subtract the extrinsic input delta L, and then you subtract this other factor 2 YLS by sigma squared. Okay. So, this is the intrinsic part. When you subtract these two, you are going to get the extrinsic output LLR, which needs to be sent to the second decoder. Okay. Yeah, this is the scalar LLR for the intrinsic component. Okay. So, this is like the scalar LLR that we had before.
So, in the extrinsic output LLR, we are not completely eliminating the extrinsic input too, sir, because the alphas also to some extent, alphas and betas also depend on the.
Oh well, it's not really true. See, look at it. So, you're saying
Alphas are calculated from the previous branch matrix, which actually.
Okay. So, you're saying the extrinsic, okay. So, you have to eliminate the extrinsic input in the Lth stage. The extrinsic input from the other stages can filter through into your Lth stage. That is okay. 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 So, the question here is interesting, and you have to pay attention to the question. The question is, so we are saying we are subtracting the extrinsic, but that is on a stage by stage basis. You do not totally subtract the extrinsic out, you should not be totally subtracting it out, because there is a trellis dependency on this information and you have to exploit that trellis dependency. Okay. So, in your Lth stage the other extrinsics will feed into it, the other channel information will also feed into it, all those you are not going to subtract from your Lth stage. In the Lth stage you are going to subtract the extrinsic you received for that stage and the channel systematic received value for that particular stage only. Okay. So, of course, not just the extrinsic, even the ys that you received for L minus 1 will feed into this, all that you do not subtract, that you use, but in the Lth stage explicitly you subtract what is coming through. Okay. So, that is the I mean if you think about it, that is an approximation in your iterations. Okay. So, there is some dependency that will carry through, you are not really subtracting all the dependency, but if you account for all of that then your decoder is becoming optimal. You do not want to do optimal because it is going to become really huge, I mean this is not going to be implementable. So, that is essentially the approximation you are doing. Okay. So, you feed in something, but since it is through some other path, eventually the dependence will hurt you only after a few iterations. So, if you have converged already by a few iterations you are happy, that is the idea. Okay, but that is an important point to keep in mind, you do not throw away all the extrinsic in, but only that in corresponding to the stage. Okay. So, now we have filled out all the necessary details for the turbo decoder, which is here. Okay. Once again I am sorry for this notation, I guess I wish somebody had pointed out that this should be R instead of Y. Okay. So, Y was after the BPSK, so I think here I made the mistake came here, right. So, after BPSK it should have been, oh, BPSK plus AWGN is how I am using, okay, I should not have done that, no, okay, I should have said after BPSK it is Y, after AWGN it is R. Okay, if I had done that and then everything would have been very hunky dory again, but anyway it went off for a toss, that is okay. So, hopefully this thing did not pain you too much. Okay, so, now we have all these inputs. So, if you had taken the pains to implement the BCJR algorithm like I asked you to do last time, but maybe not enough of you did it, then you can now modify that implementation to add using extrinsic and computing extrinsic. Once you do that, you can even implement the turbo decoder. Okay, so, it is not too scary to implement, right. If you are good in MATLAB and you write a MATLAB code for this, it will hardly take about 40-50 lines, that is it, you can finish off your turbo decoder implementation. Okay, that is all it takes to achieve or at least approach capacity with finite FEM. Okay. Any questions on any of these computations? Okay. So, one question to ask is, this is very much a BPSK computation, right, if you look at it. Okay, I have strongly used some BPSK properties, what happens if it is not BPSK, etc. Okay, those are questions you can ask, but there are things you can do, okay, so to work around that. But today what you do is you how to get down to this this kind of a thing is to kind of approximate things like so that they look like BPSK and then you try and work around it. So, that is the idea. So, usually I mean there are some additional tricks needed to deal with arbitrary QAM constellations, but we will not go into that. BPSK is at least straightforward. Okay. All right. So, what we are going to do next is maybe see a few more. So, I have had several students work on implementation of turbo and LDPC codes in hardware, okay, and there is a couple of theses particularly from last year or year before that, 2 MTech students who did a very good job with implementing LDPC and turbo codes in VLSI. And is there a USB port here? Okay. So, okay, so what I am going to show, so you see there is a turbo 3GPP thesis, that is from a student named Mudassir, 2009, so that must be last year or year before that, last year. Okay. So, we are not going to look at this entire report, but okay, why is this? So, let us go through the main part of the part I want to show you. So, this is the, well, so this is, can you see it very easily? Maybe I should do this. This is better. So, this is the 8 state 3 GPP turbo encoder. So, 1 plus d power 3 by 1 plus d squared plus d power 3. You can see the feedback is 1 plus d squared plus d power 3, and what is taken out is 1 plus d power 3. And this thing fell on my lap. I thought it was some cat or something. Okay. And then you have the interleaver. Okay. So, this is the picture of the, so this is what he implemented. He put this. So, these days I think, I do not know how many of you do Verilog, VHDL or anything like that. It is almost like C programming. Write a program and press compile, it becomes an FPGA implementation. Okay, so, something like that, but of course, he did a lot more stuff than that, but that's one way of thinking about it. So, that is the trellis, there are some things. So, in fact, they terminate both actually. So, here is a picture of the, here is a picture of how the encoder would look, all extrinsic, intrinsic, etc. Okay. And then the turbo decoding algorithm, there are all kinds of pseudocode. Okay, so let me quickly go to the part that I want to show you. Okay, the hardware implementation. Okay, so there is lots of stuff you have to take care of when you implement. So you see this max star versus max, right? So you can see the formula that is there. Okay, and then okay, so hardware implementation. So let me show you. There is like a, this first the windowing part. Okay, so he's talking about sliding window, max log map. Okay, so okay, so I'll come to this maybe a little bit later. So let's look at performance comparison. This is quite important. So, okay, so okay, why is this going so fast? Oh my goodness! Oh my God! What did it do? Oh. It's really took off. Huh? Must have been really upset with me for something. What? Too sensitive. Computers are becoming more and more human, sensitive, you know. Okay, so this is what I want to show you. Okay, so the first thing to keep in mind is, so when I write down the algorithm, in the way I write it down, I am treating everything as a real number, right? I am treating everything as a real number, but real numbers do not exist. There is no such thing as a real number. It only exists inside your head and you can work with it, but in practice there is no real number, right? In computation you can either use finite precision or floating point. Okay, so those are the only things you can use. Only a finite number of numbers you can deal with. Okay, so the first thing is to do a floating point implementation. Okay, why is floating point the easiest to do? You can write a C program or a MATLAB program, it will naturally do floating point. If you want to do fixed point finite precision, you have to do some additional effort to make it fixed point finite precision, right? So floating point is the first thing you implement. So you see, for instance, this plot that he has here is for the, if I do this, will it go up? No, it does not go up. Why does it go up? Okay, so let me zoom into this plot and show you. Can you see that? Is that good? Okay, so that is the first plot I am showing you. So this is bit error rate versus EB over N naught for a rate 1/3 turbo code with 5 iterations. You can see that in the title, and the length is 1152. That is the maximum possible length in 3GPP, and he has simulated 10,000 blocks. Okay, and you can see here there are 3 different decoders. One is called log map. Log map is basically basically BCJR, complete BCJR. Next is max log map. There instead of max star you do max. Okay, so you do not use the sigma squared. There is lots of benefit in that. So you see there is about like a, if you look at it, loss at 10 power minus 6 bit error rate. What is the loss? Roughly about 0.4. Okay, sort of maybe 0.4 dB loss from log map to max log map. And then he has a SW. SW is basically sliding window. Okay, so 1152 is a long length. Okay, you can't store, even if it is fixed point with 8-bit precision or 10-bit precision, that is a lot of bits to store for alphas. Okay, so you have to do sliding window. Okay, and that is where he had this picture. I thought that was a good picture to show how the sliding window works. Okay, so you can see the picture on the top. So it's got this one forward recursion, right? You start at 0 and go up to w minus 1, which is actually a window width, but you do not stop there, you go all the way in the forward recursion up to w plus l minus 1. So there is the extra l that you have to go, and then start your reverse recursion from w plus l minus 1 all the way down. Okay, but you make decisions only from w minus 1, you can't make decisions from there. Okay, so the same thing you do, then you continue the second forward recursion from where you left off, w plus l minus 1, and then the backward recursion will go all the way down to w minus 1. Okay, and then you start the computation. So you have to overlap your windows like this. It's just a small trick, but you should do it carefully. Okay, the crucial parameters are w and l. Okay, what w you pick, what l you pick. Okay, all these things you have to optimize in your simulation. So what do? How do you pick w and l? There is no theoretical formula, right? So you first pick different w's and keep plotting and see which gives you the good performance. And he has done a whole bunch of that. So I will show you what all that he has done. The first thing is this. Oh my god. Oh my god, oh my god, just goes. Okay, I think the hold and grab for some reason is not working, right? Okay, so the first plot he has done is that, and then there is a sliding window that he has done. He has not put down here what is w and l, but I think he has optimized it later on. There is other plots for that. Okay, so the first thing I want to point out is at what EB over N naught is it achieving 10 power minus 6. Look at that, 1.1. Okay, uncoded is at 10.5. Okay. What kind of gain is that? 9.4 dB coding gain. Okay. It's huge. Okay. Of course the rate is 1 by 3, maybe you do not like it too much, but still coding gain is huge. Okay, in EB over N naught, of course rate is being accounted for in EB over N naught. Okay, so that is how turbo codes work. Okay, so they are really very nice. Okay, so now let us start looking at the other things. What else did he do?
Capacity at the rate,
1/3 is maybe less than 0, it is about minus something, minus 0.5 maybe. Okay, so here he has looked at effect of what he calls as guard window. I think guard window must be the L. Okay, how large is L for a fixed W? W is fixed at 64 for some reason, and then he is looking at G4, G8, G12, G16. So L is 4, 8, 12 and 16, and you plot different things. Okay, as you increase L, of course, as you increase L, the performance becomes better and better. Okay, at some point it will start bunching. Okay, so you see the bunching is happening at 12 and 16. So you pick something like 16 as your the lag or the what he is calling as guard window. Okay, the guard that you have to do to make sure you get good results. Okay, so this is what you do, this is how you design. Okay, if you go to a company or something and you have to implement a turbo code, this is what you will be doing. First you write a MATLAB program and then you test all these parameters. Okay, you simply keep simulating it, different parameters, plot these curves keep on, you have to plot and pick the different parameters to give you a good performance. Okay, so this is for effect of guard window. And then quantization. Okay, so the quantization is the next part. Okay, no, before that he has done number of iterations. Okay, so how do you stop? How do you know when to stop? How many iterations do you do? Okay, so you plot probability of error after first iteration. Okay, this also I think points out, this also nicely brings out the effect of the turbo principle. Okay, the first iteration, look at the curve, right, the topmost curve, it is not doing anything. By the time you do 5 iterations, what has happened? It has taken a drastic fall. Look at the gain from the first iteration to the 5th iteration. Okay, it nicely brings out the turbo effect. I mean, how the iterations really improve the LLRs. Okay, so we made a decision to stop at 5 iterations after plot like this. I think 6th iteration will give you very small benefit. It will start bunching. So at that point you pick your number of iterations as 5. Okay, and this is still floating point. And I think and then he did some histograms. I think I don't want to go into details there. Okay, and this is fixed point. Okay, so he has got Q4, Q5, Q6. I don't know what it means really, but 3 different ways of quantizing the received values. Maybe one is 4. I think it's not 4 bits. It's maybe there is a common 3 part and then it is either 4 bits on top of that and then another 5 bits or another 6 bits, okay, something like that. Okay, so 3 different quantizations and then floating point. Okay, floating point is just about the best you can do in computation, right? Nobody has found another way of representing real numbers or something like that to beat floating point. So floating point is really good. So beating floating point with finite quantization is hard. Okay, you have to do really a lot of work if you want to beat floating point. So floating point you can take as the standard. Okay, so that's the leftmost curve here. Then what do? You slowly increase your quantization, number of levels that you are using to make it infinite precision, till you get sufficiently close performance to floating point, and that point you can stop. Okay, right. So he has found that Q6 for instance is very close to the floating point line. So you pick that Q6 as your quantization level, okay, and he has used W is 128 and rate is 1/3, etc. Okay. So this is how you pick each and every one of your parameters in your decoder. Okay, all these things are important in practice. If you are implementing a turbo code, you have to worry about how many bits are you going to get per symbol. You will never get floating point. Okay, so after all there is some analog to digital converter sitting there which converts the samples into digital data for you. Okay, it cannot be more than 8 bits. It's very hard to imagine anything more than 8 bits. Okay, so 8 bits is a good number to think of. And then for that quantization, how do you implement your turbo decoder? How does it work? All that you have to study. Okay, so each and every one of these aspects you can study, and again you have to go back to the simulations. Okay, unfortunately it's not a code which has great structure where you can just analyze and get some data out. Okay, you can't decide number of quantization intervals without doing simulations. It's very difficult to do that. Okay. Okay, what is this? This is for rate half. Okay, again rate half, the 3GPP will specify how to go from rate 1/3 to rate half. I believe it's even and odd puncturing. When you do that, you go to rate half, and you see there is, it's not as good as rate 1/3, right? The coding gain is dropped. Okay, right? But then you gain in rate, you go to rate half. So but still there is significant coding gain. Okay, you get 10⁻⁶ bit error rate at around 2.2, 2.3 EB over N0. That is still about 8 dB of coding gain, okay, at rate half, which is really good. Okay, if you remember the best convolutional code plots, they were at around 5 dB, 6 dB. Okay, so it is still like this huge 3 dB gap from the regular convolutional codes that you are using at rate half. Okay, and with again Q6 quantization, as he calls it, I do not know exactly what Q6 is, but Q6 quantization is able to get very close to floating point. So you pick that as your point. Okay, so this is rate 2/3. This is also specified in the 3GPP standard. Okay, once again you do similar curves, and you see there is some kind of a flooring effect that you can kind of see at rate 2/3. Okay, so it doesn't. This is what I mean when I say it's only for finite FER, of course. Okay, so you can't really avoid these floors. Okay, so you get this, and that's about at 3.3 dB or so. Okay, for rate 2/3, again a significant coding gain and a higher rate. Okay, so these are plots that you have to do. Okay, all right. So after that you can optimize power. That's something that he did. But anyway, so the general idea I want to convey is, if you are implementing turbo codes in a company or for any other purpose, you will make a lot of plots like this. Okay, so you have to create plots like this to justify your design choices. What are the various design choices here? To decide about window length, right? That's a very practical thing to decide on. How many bits you are going to put per symbol, that's something you have to decide. How many iterations you are going to do. Okay, all these things you have to decide based on these kind of simulations. Okay, there is no way around it. Oh, 3GPP specifies the interleaver, it is the QPP interleaver. Okay, so usually in the standards the interleaver is specified. So the standards will completely specify encoding. What do they don't specify? The decoding. Okay, so that's where you have to do. Okay, the receiver is what you have to build. Okay, transmitter is usually standard. That's what's standardized. Okay. Of course, there will be decoders available, I mean implementations available, but it's good to optimize. Okay, so this is for the turbo code. I wanted to show you a similar thesis for LDPC codes. In fact, both these guys work together, and they were kind of competing with each other to see which is better, LDPC or turbo. Okay, so that was the kind of competition that we had, and anyway, both these guys did some cool stuff. They were both VLSI MTech students, not communication MTech students. So you're saying that's why they did good work? Or? Anyway, both these guys, I think Kiran is working with, I can't remember, Mudassir also working in, both of them are working in Bangalore doing more VLSI stuff. Okay, so let me see, I mean where this has come, this will probably come much later, maybe I can use this, when I want to, it is not going very fast. Okay, so maybe okay, no, this is not what I want. Okay, so maybe it is here. Okay, yeah, so this is what I want to show you. So this is 802.16e, which is the WiMAX standard. I believe the WiMAX, I mean .16e you have the LDPC codes, but WiMAX has chosen not to use it. Okay, maybe others will use it. I think it's maybe even optional. I can't remember what the exact situation is right now. Okay, and Kiran implemented min-sum decoding. Okay, he did not implement the full scale one. Okay, so here's the first plot that you see. This is a floating point simulation for a rate half LDPC code. I believe iterations is 10. Okay, and then I think the block length is, oh my goodness, my goodness. Huh. Okay, so let's zoom in a little bit. Okay, so this is a floating point simulation for a rate half code. I think, I mean, I can't remember the block length, it does not seem to have specified it anywhere. Maybe later on we will have those things also, but this is min-sum decoding. Okay, and also the turbo simulations I showed were always max log map, they were not log map. Okay, so max log map, and you can see similar pictures. Okay, so you have there are two comparisons here, one is min-sum and another is offset min-sum. Okay, offset min-sum is slightly better, and you can see about 2 dB you are getting 10 power minus 6 for rate half. Okay, which is roughly what the turbo code also did. Okay. So for, if you look at rate half, turbo code, LDPC are roughly the same, okay, in terms of performance, and in fact the rate 1/3 you will never have LDPC code, so it just becomes very inefficient at that point. Okay, it's better to do turbo if you want to do rate 1/3. Okay, so again, once again, effect of iterations, how do you decide how many iterations to do 6, 8, 10, 11, 12 till you see the bunching up. This is all LDPC, remember it is not turbo anymore, doing LDPC, and you do these simulations till you see the bunching up, and you can see about 12 iterations seems like a good number to do. Okay, and then effect of quantization. Okay, once again you do 4-bit quantization, 5-bit quantization, 6-bit quantization, floating point, see when it gets close and then you pick it. Okay, effect of rate, he called it effect of rate. Okay, so anyway, it does not matter. This is again 2304, I think the block length is fairly high, okay, 2000 or something, 2300. Okay, and you can see there are rate half, rate 2/3, rate 3/4 and rate 5/6 codes. Okay, in the standard, this is block length 2304, 10 iterations is done, and you can see the curves. Okay, so about 2 dB, around 2 dB you are getting 10 power minus 5 here, about 2 point, I don't know, 7 or 8 you are getting 10 power minus 5 with the 2/3, for 3/4 it is just 3.4 or so, and even 5/6 it is about 4 dB, it is at 10 power minus 4. So, it is quite good performance for LDPC code. So, in fact, if you compare the rate 2/3 code, you will see the LDPC code is doing better than the turbo code for corresponding length. Okay, so it's for higher rates in general it is easier to design LDPC codes, because you have to do, for turbo codes you have to look at a lower mother rate code, then you have to puncture, etc. Okay, that turns out to be a little bit more suboptimal, and this is something that you can do in LDPC. So that is the plot, and then this is code word length. Again, this is again an interesting lesson. Okay, the same I mean the LDPC code, one specified for code length of 576, another is for 2304. Okay, same rate half, and look at the difference. Okay, 2304, 10 power minus 5, around 2 dB, length 576, it goes all the way up to 2.8 dB. Okay. So, the longer block lengths are always better, okay, in turbo LDPC codes. So, longer you go, it is always better. 576 I believe is the smallest length specified in the WiMAX .16e standard. Okay. Okay. Anyway, so I think that's it. I think then he talks about synthesis results and all that. Okay. So what am I trying to convey by showing these two theses? Okay. So, the main idea is if you are in the business of implementing these things in hardware, you have to worry about a lot more things. Okay. You have to worry about many things, but essentially the algorithm will not change, it will be the same. Okay. So, you will have to make decisions such as number of iterations, number of bits per symbol. All these decisions are made using simulations, that is all. You have your basic decoder working in fixed point, then you can make all these decisions. Okay. So, try anything you like and then pick the best case and then you implement. Okay. So, this is what you do if you join industry today and you are building codes, this is the kind of work that you can expect. Okay. All right. So, I think that kind of concludes the, hey, where is my Windows journal? Hey, what is this? Leftmost button?
All time you can't do.
Hey, what? Why is this? What do I do, man? Any ideas?
Open it up and
Open it up and press Alt tab.
Alt tab.
Alt tab.
Oh, okay.
start button.
That's the one. Wow. Hey. Finally, everything you do becomes an adventure. See, this seems very well behaved with the pull, but that thing was, the Adobe reader was very bad. Okay.
LDPC does better and some rates Decoder does better. So in general, actually, when the SNR is bad, there will be rate fall back, right? So that's when we change to the lower rate. So can we change even the coding? We can that also be changed.
Yeah, I think okay. So the question you're asking now, a question about the standards as opposed to the codes themselves. Okay. Yeah, I don't know. I don't know what the standards allow. I don't know if you can switch from LDPC to turbo or something, but usually, yeah, it should be possible. You're right. Okay, rate 1/3 maybe is the lowest, and beyond rate 1/3 also they do. In fact, what they'll do after 1/3 is they'll do repetitions. Okay. So beyond 1/3, you give up hope on code design. You simply do repetition. Okay, keep on repeating. Anyway, there's an absolute limit on EB over N0 beyond which you can't do anything. That is something like minus some 1.69 or something. So you can't do anything below that. So if it's below that, you have to boost up something else. So yeah, 1/3 is like the lowest code rate you'll see in standards. Very few people go below 1/3, and LDPC stops at 1/2. Very few standards go below 1/2 LDPC. But remember, believe me, 1 dB, 2 dB, and all is really low SNR. You're looking at very low. In EB over N0, that's really low. Most systems will work at around 3, 4 at least. At least you'll adjust your power budget that way. You wouldn't bet on 1 dB. 1 dB will be like the extreme case when everything else has failed, it can still succeed kind of situation. At least that's what I know about wireless standards. You have to ask somebody else who knows more about whether you can switch or not. Okay, so let's a few seconds left. So let's quickly summarize. So LDPC and turbo is what we have looked at. Okay. And there are some general principles which I spoke about very briefly, but let's not we'll get into that in the next lecture maybe. But in general, these are in standards, they will continue to be in standards, and there are lots of implementation issues which are very interesting that people still work on. Okay, so implementation issues that people still work on, and most of these choices are done based on simulations. Okay, simulations play an important role. and can there be a nice theory? I do not know. Okay, that is the first question. For implementation, at least nobody bothers with the theory. If you can do it, it is fine. And the one thing to remember is, usually when you meet people, everybody talks about LDPC and turbo as being capacity approaching. Okay, so you should know in what sense these are capacity approaching. What is the sense in which they are capacity approaching? Okay, they can achieve finite. Okay, the important word is finite, low FERs. Okay, close to capacity. Okay, so you should remember, first thing you should remember is, as long as you stick to finite block lengths, you can only achieve finite error rates. You can't go below finite block length. So the issue here is, suppose if I let my block length go to infinity, can I still get arbitrarily low FERs? It turns out not all LDPC codes do that. I mean, you can't show capacity of achieving. Okay, there is a gap to capacity at which today people have been able to show that you can get arbitrarily low frame error rates for LDPC codes. Similar thing is true for turbo codes. In turbo codes, in fact, much lesser theory is available. LDPC is a little bit better in terms of theory, but the state of the art today is you cannot show arbitrarily low block error probabilities for arbitrarily long block lengths and getting to capacity. If you are willing to be a little bit away from capacity, not too far, a little bit away, then you can show arbitrarily low frame error rates for LDPC codes. So that is the kind of situation that people are in. Okay, and of course deterministic constructions are still open. Okay, so far people do these random looking interlevers. Even for LDPC, it is random computer search based design. Okay, deterministic constructions are still unknown for these things.